For the YouTubes, I just finished being very kind and patient with the classroom about assignment 3, and I wish them the best of luck, right? Because I'm done. So today we're going to discuss object magic, right? And I didn't invent this term. I don't know why they chose it. Occasionally, like mostly we choose words that make sense in some case. This one's just, I don't know, someone trolling us. So we defined some objects last week. And among the objects we were writing, we always had this method, which is a name for a function that belongs to an object. Everyone had this initializer method. And this initializer method is known as a magic method. And the magic methods are named using this sort of bracketed double underscore. So names like this are reserved for magic methods. There are other cases where you can use the underscore. I don't know if you remember at the beginning of the semester when I was going through the PEP 8 manual saying, oh, like capitalize this and don't capitalize here. And I said something along the lines of never begin variables with underscores. It's because they're reserved for instances like this. There are at least 5 different ways you can use underscores. 3 of them I would have to explain more than they would reveal. So I just picked these 2. We use an underscore as an anonymous variable. But it kind of bugs me because, okay, I'll show you why. So I can do this. A perfect time for this, by the way. Boom. Okay. Okay, so first I should say none of the following that I show you should be surprising because it turns out you can just set this, right? That this is just like a word like any other. So, but it does have some special functionality. You could be working in the terminal like this, and suppose you now feel that you need to do 2 to the power of 5, and you're like, crap, I should have stored that as a variable. I'm going to need to reuse it. You, in fact, can use underscore to get the last thing that was calculated. Right? So I can do something like last thing that was calculated times 2. Right? Okay, last thing that was calculated times 3. Store the last thing that was calculated. Right? So when you're working in the Python interactive mode, the underscore is a handy notation to get the last thing that was calculated. That is quite useful in other instances. The other place where we want to use it is when we need to put a variable somewhere, but we're not actually going to use it. So suppose we just want to print something 10 times. We would normally say something like for x in range 10, print hello. But you see, we never used x. We never used like the iterator. In this case, it's more appropriate to do something like this. For anonymous variable that I'm never going to use, or print hello. Right? It's also used in situations like this, where you want to say x. Suppose I have a point that's like 1, 2, 3, and I want to decompact it into x. I don't care about y, z. Then you can do that as well. Right, so the underscore is also used for this anonymous type of notation. So here's, again, the initializer method that we made last week. So when I actually create an object, there's a special name for this. It's called instantiating the object. And it's called instantiating the object because the technical terminology for working with objects is that you create an instant of the object. Right, so you instantiate an instant of the object. So it's just some verbiage that we're going to have to get used to. So when I say I instantiate this object, you can just hear me say I created the object. So here are the 2 ways. Well, here's the first magic method that we worked with, this initializer. Let's just create it in Python. So we want to make a class. Let's call it a point. We have our first magic method, the initializer, which takes in, and let's just initialize to x, y. And we'll say self.x is x, and self.y is y. Okay, so now I can go in, and I can instantiate a point. So I can have point P is the point 1, 2. So the first thing I want to deal with today is the fact that the information being lifted by Python to the user is useless, right? I know that this is a point, and knowing its memory location isn't very useful to me. So what I would like to do is have Python print something more nice than this. And there are two magic methods that will allow us to do this. Now, first we have to distinguish between what I did here and what I did here. So notice, right, that we have two types of representations of stuff. Okay. This is a representation of x, and this is the string representation of x. Right? One gets printed and the other one gets lifted. Right? One's represented as a string. So we have to tell Python what to do in two cases. What to do when the user just asks for information from the interpreter, this, and what to do when the user asks to print, which is this. Now, I'm going to try to write a program that's going to help us work with matrices on Friday. And with matrices, there's really a use case and justification for printing something different than what you represent. Right? Normally, it is the case that the representation and what you're printing is exactly the same thing. But what happens if we're working with matrices that are like 1 million by 1 million in dimension? Right? It's not very useful to print that to the screen. What would be more useful is to print something that says, so I create a matrix and I ask Python to give me some information about it. It'd be better to say something like, this is a 1 million by 1 million matrix with integer entries, right? Or if the matrix is small enough, then you can print it. So the two magic methods we need for this are string, 1, 2, and representation. So this is what gets printed in print, right? When printing, and this gets what I call lifted by Python to the user in the interpreter or interactive mode. Okay, so what should our string representation look like? Well, let me start with the string one. So this is what's going to print when we ask something to print. So I think I'm going to do this. Self.x, go away. Self.y. So yesterday I used these kind of brackets with the other class, but that ended up messing with us because they look exactly like tuples when I print them like this. So I'm just going to invent a new notation. I'll just do this. We're going to use the angled brackets for our points, right? Just so we know something different is being printed by the console. Okay, so now I can make p a point. I can give it some value. What? Oh, I didn't actually return none. Here's our point, and now I can print p, and it does that, right? Already more useful. So here, this is what's going to be lifted by Python to the user. So the string representation really is for end users, whereas the representation are for programmers, like the technical people. So maybe this can say return a point in R2. Oops. So now we have a functionality that sort of looks like this. P equal 0.23. P is a point in R2. If I print P, it looks like this. Okay. So what I'm going to do, though, is just grab this so that the print representation and the representation is the same thing. I just wanted to show you that they don't have to be the same thing. But actually, for our case, it is better just to have it so I can do this. Right? So now I'm actually printing something rather than just printing out that this is an object and its memory location. Oh, good God, that was hot. Oh, and I drank way too much of it. Oh, my stomach's on fire. Oh, boy. I'm okay. I will survive. What would you do if I wasn't? Call an ambo or something. Okay, so here's the stuff for the string representation. Here's the stuff for the representation. Add. Okay, so there's there's tons of magic methods, and in Python, this is really what makes objects and classes worth working with. So now that we have points, I want to be able to do arithmetic on those points. And the point of objects is that we don't use functions. Functions is the other type of approach. We want to have the objects have to handle the arithmetic themselves, right, without user intervention. So I could say what happens when we add 2 points together. Now, who has previously done object-oriented programming? Okay, so you guys are probably used to doing something like this, right? Declaring a bunch of variables which are scoped to the object at the beginning of the object. We don't have variable declaration in Python. So we don't have variable declaration here. That's the whole point of this self object, right? That you're saying that I want to modify the value of myself. Now, add has to operate on 2 objects, right? Add is a binary operation which takes 2 things and returns 1 thing. So you take yourself, but you're also taking another object, right? So add is going to take 1 object, myself, and another object, some other object. Now, let's just add points together in the obvious way, where we just add the components point-wise, right? So the sum of the x components and the sum of the y's. What do I return here if I want to sum the points? Is that it? Those? Yeah. I'm just asking the rest of the class if they agree with you or not.
Or we use like the string with the chevron notation points. Maybe we should be consistent.
So raise your hand again if you've done object-oriented programming. Yeah, less confident now. If you don't know what to return here, you really haven't done object-oriented. You really haven't understood the purpose of object-oriented programming. Yeah.
Should we return a point?
Exactly. Right? Well, you need to stay within the paradigm. It doesn't make sense to take 2 points and return a tuple. Right? If you want to represent points as tuples, represent points as tuples consistently. Right? But we've created an object for point. Right? So 2 things, an operation on a point should return a point. Right? So I fear most of you have just used objects as a structure. It's like, look, you can have an object which is a variable where you get access to the variable with periods. Right? That's something we have in C called a structure. That's like halfway in between like a variable and an object. This is the purpose of objects. Right? Okay, so let's go investigate what have we done here. There's a point. Here's another point. We can look at them. We can add them. Neat, right? All of that work happened under the hood, right? So you can do very sophisticated. Well, this isn't a very sophisticated addition algorithm, but you could do some sophisticated type of arithmetic, which is very simple at the user level, right? Just an add. Now, yes.
So is that add method being called on P or on Q or on both?
So the order matters. So if you do P plus Q, P will be self and Q will be other. If you invert it, then Q will be self and P will be other. Yes?
So when we define the magic add function, are we actually redefining how Python does?
On those objects only.
Yeah.
Not plus generally. Yeah. Just this object. Which is great because then you can have multiple different objects with different additions. And you can still at the user level use plus. Right? Rather than having to have a million functions everywhere, right, doing something. Right? So if I wanted to do this with tuples, in our old approach, I would have to have a function which is like tuple add, right, to take in 2 tuples and to return a tuple. This, I want to call this overloading. I'm not sure if that's the correct term, but this fact that like we can overwrite the add operator so that it actually manipulates the addition operator at the top level is Mint. You don't get this in many languages, but you can really do powerful stuff with this. Here are the rest of them. Addition, subtraction, multiplication, floor division, and true division. You don't actually need this one. Or the subtraction should always be... See these? You shouldn't define addition and subtraction. You should define addition and negation, and then define subtraction as it adding the negation of the number. It's sort of like kind of mathy, but if you get an operation and the inverse of that operation, you don't need to define both the... You don't need both add and subtraction. You don't need both multiply and division. You just need addition and negation and multiplication and inversion, right? Maybe one day I'll have you guys for an algebra class and we can really dig into these things. But in any case, you have these binary operators: addition, subtraction, multiplication, floor division, and true division. Oh, at least these ones. There's more. I just didn't want to list them comprehensively. These unary operators: negation, power. What? Power is not a unary operation. Okay, well, at least let's move power back to the previous slide. You get negation, absolute value, and inversion.
Inversion means like a reciprocal fraction.
For fractions, inversion means reciprocal, right?
For non-fractions, inversion means...
Do you really want to know? I could really tell. Think about this. Okay, I'll tell you a little bit about groups. So a group is any collection of numbers, let's say, for which you have 0 and an addition operation. Now, what's the property of the 0?
Anything plus 0 is a sum.
Exactly. So using that type of statement, what should the definition for the inverse of addition be? So if you find 2, what's 2's inverse in addition?
Still 2.
No, it's the thing that gets you back to 0. Negative 2, right? So you have 2 and its additive inverse negative 2 because that gets you to 0. Okay, that's a group. If in addition to having addition, you also have multiplication, now you have a multiplicative. Okay, so the 0 was the additive identity. It's the operation. It's a number, a constant, which has no effect if you use it, right? So anything plus 0 gives you anything. Anything times 1,
That's the multiplicative.
right? So 1 is the identity operation for multiplication. So inversion, you give me a number, x. I have to find another number, y, such that that product equals 1, right? That's the definition of inversion, right? You said it yourself, reciprocal. What's a fraction times its reciprocal? That's how you define inversion, right?
You have both.
Both what?
Like what if you want to do a negative reciprocal? Like
Well, then you need to study algebra to understand why, because eventually you're going to add so many restrictions that the whole thing collapses into itself. Then you're like, great, you have a group with 0 and 1, right?
that's not very useful. So
Well, 0 and 1s are quite useful to computer scientists. You can go pretty far with 0s and 1s, let me tell you. But this is algebra. Like, I could go on for an hour about this. I specialized in computer algebra. But you have to understand how operations interact with one another if you want to start defining them, right? So can anyone identify a problem with the addition operation that I wrote for tuples? Oh, no. No, that's fine. There's no problem with that so far because it is commutative. I did the currency example with the other class, and that wasn't a commutative addition operation, but no one noticed. Commutative being x plus y should be y plus x. It's not necessarily the case that you should have commutativity. Division isn't commutative. Neither is subtraction. Anyways, why don't you guys all take my algebra class that I'm hypothesizing that they're going to let me teach one day. I'm also hypothesizing that they're going to hire me. In any case, we also have these comparison operators. And you really have to define all of them. Well, you don't really have to define all of them. Which ones can you skip? Right? Exactly. So you want to define the less than operator, the equal operator, and then use those two things to define the less than equal operator. Right? This one should be like it's less than or it's equal. If you want to sort your objects, you have to define at least one of these comparison operators. Right? Python needs to know how to like order one object in front of another. I think already though that Python is going to be, oh no, not yet. Okay, so let's just define a less than operator here. Self and other, right? You need two objects, it's binary. So just, how do you want to, we can make any comparison operator that we want. Okay, so let's say that one tuple is less than another tuple if we sum the individual elements, right? And then compare those scalars, right? So I'm going to do, let me think, return self.x plus self.y is less than other.x plus other.y, okay? So I can have these 2 points, point P, point Q, and now I can say P is less than Q. Should this be correct or not? So I'm saying, so I said we're summing up the individual elements and comparing that. So P gets 5 and Q gets 4, so this should return false. Yeah. Right, but this would allow us now to, wait, can I sort? Or maybe I can ask for the maximum of these? Yeah. Right, but that, I can't do this. Will this work? Okay, this means it's actually using the less than operation, but just flipping it, right? So, yes.
Does defining a less than define does defining a less than imply defining a greater than?
Let's check. No. But it seems that max and min both use less than to do the ordering and then pull out the thing. Yeah.
Do we really need to use the not equal sign if we have both greater and lesser? Because anything that's not equal to something else, either greater than or lesser than it, it's strictly math.
What if I'm doing like clock arithmetic or something? Like, I'm telling you, there are cases where weird things may happen, right? Like matrices. How do we compare, like, is one matrix, like we may not get any comparison operator, period, right? It may not make sense. Like, what happens if I'm like, I have an object for polynomials? Like, what does it mean for one polynomial to be less than another polynomial? Right?
The highest degree is less than the other.
Yeah, sure, we could come up with, okay, so you can order them reverse lexical graded, right? And then we're off to the, I also love to teach you guys a computer algebra class, but the point is now that you get to define all, like you're basically getting access into algebra here, right? By defining less than operations, addition, subtraction, stuff like that. So that's why I want to do matrices with you on Friday. I think that'll be a good example. Okay, so we have maybe 15 minutes. I have 3 questions that we could attempt. We'll probably realistically only get through one of them, and you guys can do the other 2. So I'll give you guys options as to which one you want to do. So, do you guys know what a queue is? Anyone from across the pond here? Okay, like literally everyone else in the world except for us Americans. Call it, do you know when you like go to Timmy's and you're waiting for your coffee? You know how we line up? Everyone else in the world calls this queuing up for coffee, right? So we have a data structure which basically is the analog of that, people showing up to wait in line for coffee, right? So I want to create an object which basically is a list, but this list has restricted access. All you can do with this list is queue someone, that means someone goes to the back of the line, and dequeue someone, that means you remove someone from the front of the line and you service them and you take them out of the queue. So that's option 1. Option 2, we implement a class for currency. And what I want to do here is I want to have maybe like a currency object that takes a value in a currency. So I can have X Canadian dollars plus Y euros, and I want to add that at the interpreter level and have that return a value in Canadian, right? So that all the conversions happen under the scenes, which is fairly cool actually. And the last one is write a class for working with fractions. Right? That's not easy either if you start to think about working with fractions and, well, we could go through and develop fractions. Right? We could have the arithmetic to add fractions together and simplify them and invert them. Right? So which one? That's what the last class wanted. Are you picking this because it's a lab? Because I'm just going to put the other 2 there then. So this is not going to save you from doing lab work. Fractions? Fractions. Okay. You know what my response to that is? That's how much like, yeah, how does it feel? Right. Okay, let us do fractions. Do we have a GCD operator? I don't want to write it because that'll be complicated. Can we call this from math? Great. Do you guys know what the GCD is? Okay, good, because you guys know we'll need that for simplifying our fractions. Because if we don't simplify our fractions, things are going to explode. Fractions. Or maybe we should be more adult and call them rationals. Okay, so what do we need to initialize a fraction? Probably a numerator, which integer, and a denominator, which is a integer. Okay, so we want self.numerator. That's going to be irritating to type, but whatever. Is the numerator, and self.denominator is the denominator. Okay, so before I call this in, let's decide on some representations. Self and self. How should we print a fraction? Or, sorry, we should also simplify these, yeah? So now I need the greatest common denominator. So I need to do, okay, so the GCD is the GCD. Okay, I want to do this. So I can do this. So I got the GCD of the numerator and the denominator. That means I should put this up here. I need to do numerator integer divide the GCD, and the denominator integer divide the GCD. Okay, let's not be too fancy today. It'd be nice to be able to print the fractions like 1 over 2, but that would take long. So let's just do this over this. Unless someone can find the division symbol. Maybe I can try to find it. Oh no, don't open all that. You don't need to. One day something truly embarrassing is going to happen. All right, so I can try that. Format self.x, self.numer, self.denominator. Okay, and same for this. Okay, so let's try reading this in. So I can have a rational number p, and let's do 2 quarters, because this should automatically have changed this to a half. Maybe I don't like that. Maybe I want to do this. Let's see if that looks a little bit better. Okay, a half. Okay, let's do multiplication first, because that's actually easier than addition. So self and other. So what do I need to do now? Okay, so the new numerator is going to be the self.numerator times other.numerator. And the denominator here is going to be self.denominator times other.denominator. And then I have to find the GCD of these. Math.gcd, numerator, denominator. And then I need to return a rational point. Yeah, see, someone learned something. Numerator divided by GCD, and denominator integer divided by the GCD. Let's do one more. I can't remember what it was called, though. I want to do inversion. Was it invert? Yeah, invert. Invert self. That should just be numer get self.denominator. Huh?
I think you need to do the 2 plus sign because then like you're saying or when you reference numer like that without self, it's own variable, or is it?
No, I defined a new numer.
Oh,
All right. So this numer and this numer are different. This is self.numer and this is numer. I hate this as much as you guys. I always forget to put in self, but we're all just gonna have to cope because that's just what it's like. Okay, this should be numer, so I've inverted it, but I still have to reduce these things. So GCD is equal to. Okay, so you see now that I have done this basically everywhere. This is a good indication that I should have written some type of method to handle it, but not today. Numer and denominator. Yes.
In your inner function, you already divided it by. Oh, no.
If I invert, I may have to do another. Oh, no. No, I don't.
Yeah, lowest common distance.
Yeah, you're right. I don't actually have to reduce this. I just have to switch. Okay, and I did this just so I could define division, which is called what? True division. Okay, true division of self and other. And someone give me the lazy implementation of this.
just multiply by the inverse.
Right. So I want to return self negation. Oops. The inverse of. I don't actually know if this is going to work. Because I may have to say self.invert at this point. Okay, so I'm going to come back to this. Maybe never. Let's see how far we've gotten. So P is a point. P is a rational 3/9. Okay, so we got 1/3. Q is a rational, maybe 3/7. Great. So now I want to have R, which is P times Q. Okay, so we need to predict the output before looking at it. So it should be 3/21, which is 3/21 is 1/7. Perfect. Let's try inverting R. Great. Okay, so what I want to do, I don't know if this will work. Let's find out. True divide. Was that it? No? True divide, yeah. Self and other. Okay, so I want to do something like return negative self, or the inverse of self times other. But I'm not actually sure this is going to work, but let's check. Like, I speculate that I may have to say something like this. Self dot invert of self times self dot multiplication of self and other. I may have to do that. This would be way better if we could do this. But I'm not sure if Python's aware that that exists at the time that the object is instantiated. Yeah. No, I'm true division. A divided by B is A times inverse B. Yeah.
You're doing inverse versus A.
I did inverse A? Oh, yeah, you're right. Okay. I'm highly skeptical that this will work, but I'd be pretty stoked if it did. So P's, let's just say, is a rational number of a third. Q is a rational number of 7/2. So P divided by Q. Well, it's way better. Like, this is really clean, right? And nice, right? So, and this is how you should be doing it, right? Because you don't want to have to, what's the word I'm looking for? When you like have to keep something working. Yeah, you don't want to have to maintain multiply, inversion, and division. You want to maintain multiplication and inversion and have division be the correctness of division be a consequence of the correctness of the other two, right? Yeah, solely a consequence, right? So the crappy part is if your other things are wrong, that this will be wrong, but it'll be easier to find bugs in that case. Yeah.
Make an operation where we take a number like 7 divided by 1 and turn it into the integer 7.
It's not a bad idea. Yeah.
So when we use the till method, like, are we actually using definition inversion from the function method?
Yes. So Python must have done some pretty clever stuff when it was. Yeah, when it was pulling it into memory. But like this is why this language is not appropriate for trying to run something fast. Because I imagine the fact that we get to do this syntactically, like we're paying some enormous like efficiency costs somewhere. This is why Python is often referred to as a prototyping language. Right? You can do something very fast. It's like typically if you want to write a very sophisticated program, you write it first in Python. And then you use your Python to validate the C code you're writing. So you write some C code and you say, this C code is incorrect until I can generate random test cases with my Python code that my C code also passes. It's like I know this may seem bizarre to you that you'd write a computer program to write another computer program, but you're gonna have to create a prototype before you do the real thing. So, but anyways, I think this kind of stuff is pretty cool, right? Like we've already gotten pretty far in defining. So we're now doing symbolic computation, right? If we're doing exact computations, fractions are way better, right? Look, what is this? What is it? A third. What's its float representation?
0.32.
We can represent something that the computer can't. There is no 1 divided by 3 by Python, but we just did it. We have 1 divided by 3 exactly. And we can work with 1 divided by 3 exactly, right? Instead of losing wherever you try. Well, let's just make this very clear, right? That's not 1 divided by 3, right? Because 1 divided by 3 should give you. This is how it's going to be, Python, eh? Well, that's also weird, because why didn't we get 0.999 back? Yeah.
So I think we like copy paste that float and then multiply.
This?
Yeah.
It's rounding error, right?
The reason why I do 1.0 when you multiply 1/3 by 3 is because 3 wasn't in a fractional form or rational.
Well, so this is a good point. Look, I have this rational. You can't do mixed object arithmetic, right? You'd need more overloading now, right? To say, well, like I technically do know how to multiply an integer with a thing, right? I don't know how to do that. But that would start getting dangerous. You're like now beginning to overload like the integer definition of multiplication. Yeah.
Is there a way to like define how you want to cast your object to other types?
Probably, yeah.
Like say if I want to cast my p to integer, is there like a magic object to define?
So let's try. Let's see what happens if we try to cast p to an integer. It's trying to convert its string form, right? Because integer can take strings. So that's what it's going to do if I try to convert this to an integer. It's going to look at the string representation of the thing that it's returning and see if that is a string representation of an integer. In any case, I'll throw this up on the web. You guys can put more stuff in it. See how far you can get rational numbers. Before you leave, I wanted to define a class for working with polynomials, but I'm like way too lazy. Okay, I'll show you. I don't even know if I have it. Yes, I do. Okay, so this is the program I used to work for. What? Oh, right. I forget how to do syntax here. Okay. Oh my God. I'm going to destroy the world. Okay, you see how that printed? This is called pretty printing, right? So we need a pretty printer for printing polynomials, for printing rationals nicely, because like I also want stuff like this to happen. Oh. Well. Anyways, if one of you guys want to build me a pretty printer for polynomials by Friday, I'll use it in class and give you credit. Just email it to me. Yeah. Sure. As long as you don't check. Yeah.